During this final module, we're leaving the BACB task list a bit behind to talk about something a little more out there, intangible variables. Something intangible is something that can't be touched or seen, but the variables that we're going to talk about are still physical. We're sensitive to them in the sense that they affect behavior. And given that radical behaviorism is a monist rather than dualistic philosophy, we consider these variables to be part of the same physical environment as any other type of tangible variable. First, time. We've talked a little bit about organisms' sensitivity to time with regards to responding controlled by fixed interval schedules, time schedules, DRL and DRH schedules, and differences between interval and ratio schedules overall. Time is an interesting environmental variable. No organism has an obvious duration receptor. We see with our eyes, feel with our skin, hear with our ears, but how do we sense time? It's not very clear. Another difference between time and other kinds of environmental variables is that we can't remove time. We can turn a light on and off, play a sound and stop it, but once time has passed, we can't really do any kind of reversal of that. In addition to being a variable that can affect behavior, time is also a part of the measurement and definition of behaviors. What measurable dimensions of behavior do you think time is a part of? All of them. Repeatability includes rate, the ability of a behavior to occur repeatedly through time. With regards to temporal locus, we're referencing when in time the behavior takes place. IRT references time relative to a previous response, and latency references time relative to a preceding stimulus. Temporal extent is the duration of behavior, how long it lasts. You can even consider something like rhythm, a combination of how often and how long behavior occurs in a given period of time. Just as it's a dimension of behavior, it's a dimension of stimuli, just like color, shape, magnitude, etc. For example, an alarm rings for a certain amount of time before turning off, or I could turn on a light for a minute before turning it back off again. Lastly, time is also a part of schedules of reinforcement, primarily interval, time, and DRL and DRH schedules, but of course time is ongoing, and so a part of all schedules. Regardless of what schedule is in effect, we're still measuring rate of responding, count per time. When it comes to behavior in relation to time, one thing we can study is responding that occurs during the temporal stimulus, that is, across the passage of time. For example, consider responding during a fixed interval schedule. What does the cumulative record of responding look like? So, why does responding stop or slow down in the post-reinforcement pause after each time that reinforcement is delivered? Why does it then gradually increase in rate as time goes on? The answer is generalization across durations of time. From Iverson and Littell's text, to the extent that later times after onset of the schedule produce higher response rates than earlier times by virtue of the correlation of the later times with the peck food contingency, the pigeon's pecking is discriminated responding under the control of the temporal dimension. Prior to the generalization testing represented by this graph, the pigeon was responding during a fixed interval 10-second schedule. So, during the test, response rates were highest once 10 seconds had elapsed. When only 1 second had elapsed, responding was occurring at a lower rate. And during 8 and 9 seconds, rates were almost, if not as high as the 10-second mark. But then the response after 10 seconds was not reinforced, since this is of course a generalization test. Responding at the 11-second mark then maintained at a similar high rate, but then responding was swiftly extinguished. This shows that responding was under stimulus control of the passage of time, with stimulus generalization to slightly shorter and longer lengths of time. That was responding during the passage of time. We can also measure responses that occur after stimuli presented for differing lengths of time. In the experiment outlined here, an SD was presented for varying durations of time. Then, the house light turned on, paired with a schedule of reinforcement that was dependent on the length of the presentation of the SD. That means that the stimulus of varying lengths of time presented was actually a conditional SD. So here we have the pigeon in the presence of the black circle, which would remain present for anywhere between 3 and 30 seconds. Then, the house light turned on, paired with a variable interval schedule of reinforcement if the black circle was present for only 3 seconds. Sure enough, during testing, responding was occasioned at the highest rates following the 3-second presentation. Here's another example. White noise was presented for varying durations of time. That duration of time is the x-axis of this graph. If the noise was played for 1 second, the third press of the left lever was reinforced. If the noise was played for 4 seconds, the third press of the right lever was reinforced. The y-axis shows the percentage of responses allocated to the left lever. So of course, following the 1 second noise, 100% of responses were allocated to the left lever. Following the 4 second noise, 100% to the right, 0 to the left. But here we see a generalization gradient, just in a slightly different form. When a 2 second sound played during testing, about 70% of the presses were on the left. Even though the topography of the stimulus was the same, we see the stimulus generalization across different durations of time that the stimulus was presented. Organisms can absolutely sense the passage of time, and it can gain control over behavior. If this wasn't already a little confusing, it's about to get more so. Remember, every behavior has some quantity of time. It lasts a certain amount of time, and there's a certain amount of time between behaviors and stimuli, or behaviors and other behaviors. Temporal extent and temporal locus. So, when a pigeon pecks, it produces responses with different IRTs and rates. So let's say a pigeon is pecking a key very quickly. Then, we present 2 stimuli. They could be different colors, shapes, anything, it doesn't matter, but I've labeled them fast and slow. We could teach the pigeon to only peck fast if it responded at high rates previously. Discrimination of temporal properties of the organism's own behavior may occur. That is, a pigeon may be taught to report that they just pecked fast versus slow. And if the pigeon pecked at a slow rate, we could then teach it to peck the slow key. The pigeon can essentially be taught to self-report its own rate of response. The pigeon's own rate of response is the conditional SD. So, thinking back, what contributes to the pattern of responding on a fixed interval schedule? The passage of time since the onset of the SD or the end of the reinforcement interval, and generalization across those lengths of time. Here's another schedule-related question. Why is the rate of responding on a variable ratio schedule higher than on a variable interval schedule? On variable ratio schedules, reinforcement is directly contingent on a higher rate of responding, that is, low IRTs, whereas on variable interval schedules, reinforcement is reliant more directly on the passage of a length of time. The first response after that time will be reinforced, regardless of how fast it happens. So in consideration of time, what does all of this taken together mean for EAB? Well, it means that behavior is lawful, even when we can't directly see what may be causing it. If behavior occurs in an orderly fashion, there is some environmental variable controlling it, and we need to investigate further to determine what it is. Sometimes it's related to an intangible variable like time. This means that temporal variables could account for otherwise unexplained variability in behavior. And we've demonstrated that we can isolate and study temporal variables and the temporal dimensions of responses. It's not out of our reach, even though it's such a unique variable. Now on to behavioral pharmacology. This is a huge topic and could easily have its own dedicated class, but consider this a taste to get you interested if you'd like to study it further. Like time, we feel the effects of drug stimuli covertly. Obviously, we can see and touch pills and such, but those aren't the stimuli we're really talking about. We're talking about the effects drugs have on our behavior when they're ingested or otherwise absorbed into our bodies in some way. We can consider the effects of drugs in a couple of different ways. First, chemical and neurochemical actions. For example, different types of drugs bind to proteins in our bodies or are neurotransmitter inhibitors or antagonists. Secondly, drugs have effects on our behavior. The sensations produced by drugs can act as reinforcement, as punishment, as motivating operations. They can affect our perception of other stimuli, like time, just about any function. The field of behavior analysis is primarily interested in the behavioral actions of drugs, though of course chemical are very important as well. We just don't have the tools to study that as readily. The field of behavioral pharmacology arguably would not have developed if not for Skinner and Foerster's methodology for studying behavior in operant conditioning chambers. They focused on the replication of reproducible effects and comparison of intervention effects to stable baselines, so verification. People who study the effects of drugs now almost exclusively use those methods, even if they don't consider themselves behavior analysts. That being said, not all drugs have a ton of effect on behavior. Drugs like Tylenol, Sudafed, etc. do affect behavior, but primarily due to changes in physical symptoms like headache or congestion, not due to neurochemical interactions. Those that do affect behavior in that way, interestingly, tend to have major physical and chemical effects even at very small doses, and they tend to be drugs that affect nervous tissue, such as neurotransmitters. One drug studied early in the field of behavioral pharmacology was chlorpromazine, an antipsychotic medication. Chemically, it can cause low blood pressure, and it's a dopamine antagonist, which means that it prevents some dopamine from affecting the body. Some illnesses, like schizophrenia, are associated with high levels of dopamine, so you can see how this could be effective. The behavioral actions of the drugs are that it can alleviate some symptoms of psychosis, like delirium, paranoia, and disordered speech. Another drug studied in the 1950s was pentobarbital. Chemically, it acts as an anesthetic and also an anti-inflammatory. An anesthetic is a substance that induces insensitivity to pain. So what do you think the behavioral actions of this drug might be? Dews discovered something pretty amazing. When behavior was maintained by an FR50 schedule of reinforcement, when the drug was delivered, it overall increased rate of response relative to baseline. When behavior was maintained on an F5 15-minute schedule of reinforcement, the drug was delivered and it overall decreased rate of response relative to baseline. What? But think about it. In both cases, behavior became more sensitive to the schedule of reinforcement. Responding occurred faster on the schedule on which reinforcement was contingent on fast responding, and slower on the schedule on which speed of responding didn't matter. Pretty amazing. So, the terms stimulant and depressant are really too imprecise for our needs. Everything is contextual. Here are the data from that experiment. As you can see, the effects of the drug were also dependent on the dosage of the drug. The dashed lines indicate baseline responding when saline was injected instead of the drug. The black circles represent responding maintained by the FR schedule, and the white circles represent responding maintained by the FI schedule. When a half milligram of pentobarbital was administered, it actually did increase rate of responding maintained by both schedules. But at a dose of 1 milligram and higher, it reduced rate of responding maintained by the FI schedule. It only started to reduce rate of responding maintained by the FR schedule at dosages of 4 milligrams and higher. As mentioned earlier, a lot of pharmacological research is directed at determining whether the effects of drugs are consistent and reliable, and what the effects of different doses of drugs are. This can be approached in two ways. First, regular dosing. An amount of the drug is given, and then you would wait for the effects of that drug to wear off and for the chemicals to leave the organism's system before then trying a different dose. Second, cumulative dosing. You start with the smallest dose of a drug and gradually add more of it without waiting for a return to baseline, so to speak. Keep in mind, though, that not all drug effects are truly reversible in the first place. Consider addiction and withdrawal, for example. However, these methods get as close as possible, and you can see that they're based on the same principles of our single-subject experimental designs. One interesting behavioral finding is that some drugs have a relatively linear correlation with effects on behavior, while others do not. On the left, the higher the dose of the drug, the more of a contraction response was observed, until it reached its physical limit. On the right, as the dose increased, it was initially associated with a higher rate of responding. But at greater than about 0.8 milligrams per kilogram, it actually had the opposite effect. Drugs can also have graded or quantile effects on behavior. An effect is graded if the change in the DV is on a spectrum, like changes in rate of response. An effect is quantile if the change is all or none, off or on. In an extreme example, death. Other examples are the loss of respondent reflexes. One reflex is an animal flipping itself right side up when being put on its back, the righting reflex. At some drug doses, that reflex no longer occurs. In your life, you may have heard the terms ED50 and LD50. Those are some effects that drug manufacturers must investigate. A dose of a drug that is ED50 is the effective dose for 50% of subjects that they were tested. A drug that is LD50 is the lethal dose for 50% of subjects. Don't want that. So research is necessary to find the margin of safety. Safe drugs are those that have a fairly low ED50. It doesn't take much of the drug to have the desired effect, and a very high LD50. You'd have to take a lot of it for it to be lethal. Here's the safety margin shown on this particular graph. Incidentally, almost any chemical is lethal at certain dosages, even water. If you drank 6 liters of water back to back, it is likely to be lethal. You'd have to work pretty hard to accomplish that. But there at the bottom, 13 shots of alcohol are also likely to be deadly, so be careful out there. So, when studying drugs, researchers need to consider the drug's potency, the slope showing its effects, and the variability of its effects. Potency refers to how much of the drug is necessary in order for it to have an effect. Even if a drug has a very low potency, that's fine as long as higher doses aren't harmful. Slope shows how quickly the dose of a drug can go from effective to deadly. Variability represents how consistent the effects of the drug are at a given dose. Obviously, the more consistent the better. We want an antidepressant pill to have the same predictable effect every time we take it. We also need to know if repeated exposure to a drug will cause tolerance to that drug or sensitization to that drug. Tolerance means that the more you take of it, the less effect it has over time. So you'd have to take more and more of it to have the same effect. And remember, that can lead to a more lethal dose. Sensitization means that the same dose of a drug will have more of an effect as time goes on. Maybe this could be desirable, but it can also be dangerous in its own way. For example, an anti-anxiety medication that initially reduces your heart rate and calms you down, but with repeated exposure makes you extremely tired and sluggish. And of course, there are variables that affect the effects of drugs that are not pharmacological. For example, the organism species, the size and weight of the species, different hormones or hormone levels, and even the time of day or setting. Yes, drug effects can come under stimulus control. Incidentally, here's a fun fact. Rats don't vomit, so we'd never be able to identify that particular side effect of a drug based on research with rats. Just a little more in this Edpuzzle as we further consider the interactions between drugs and behaviors. Remember, a drug can have the function of just about any other kind of stimulus. It can punish behavior or evoke behavior maintained by the escape from itself. It can reinforce behavior and occasion behavior that has been reinforced in its presence. It can elicit behavior. It can evoke behavior. It could be important to consider all of these behavioral interactions when assessing clinical effects. That being said, we don't know the full range of effects of any single drug. It is an endless field of research. Let's also consider further how drugs can change the effects of other stimuli on behavior. For example, drugs can disrupt or enhance existing stimulus control, or improve or worsen the development of new stimulus control, make something more or less difficult to learn. For example, pentobarbital can decrease stimulus control exerted by different magnitudes of light. Drugs can also affect temporal stimulus control. Hey, both of our topics combined. Prior to the testing represented on these graphs, behavior was reinforced on a fixed interval 20-second schedule. Now, when saline was presented during generalization testing there in the middle, the expected degree of generalization across times occurred. On the left, when physostigmine was injected, the highest rates of responding were occasioned once 10 seconds had passed. On the right, when atropine was presented, the highest rates were occasioned once closer to 30 seconds had passed. In colloquial terms, the passage of time felt longer or shorter, respectively. One more example. Drugs can also affect the effects of punishment. In particular, drugs that sedate or tranquilize an organism make punishment less effective. Numbers in the top panel indicate the number of responses emitted following the first delivery of punishment when no drug was administered. So, punishment was effective. In the lower panel, the drug meprobamate was delivered, and arrows indicate when the punishment schedule was in effect. You can see that responding still occurred when punishment was in effect. In addition, rate of response on the VI schedule without punishment was often relatively higher than the VI schedule performance in the top panel. This was a whirlwind introduction to behavioral pharmacology, but I hope you can see what a rich and complex field of research it is. It's simply impossible to summarize the effects of a given drug on behavior. The effects are different on different behaviors and in different environmental contexts. The effects are dose-dependent. It can also be based on whether a drug is ingested, injected, etc. As time goes on, successive doses can have different effects. These are just a few variables to consider.